Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
It's my pleasure today on this St. Patrick's Day to welcome Yuri Leskovic, who is a PhD student at Carnegie Mellon University, where he's finishing up work with Christos Fouloutos. And you'll hear a lot more about his thesis work today on dynamics of a wide variety of real-world, large-scale, practical networks. Yuri was at Microsoft Research on a couple of occasions. He actually did an internship with Natasha Milik-Freiling in Cambridge when he was an undergraduate. And from there went on to work with John Shaw Taylor doing another internship. He's probably one of the few people who's done internships with Natasha, John Shaw Taylor, and at 3 of the large industrial research labs in the spare time in his over the summers. Yuri loves to work with huge graphs. When he was here, he worked with me and Eric Horvitz looking at large-scale web graphs. And that wasn't enough. That didn't burn enough cycles and memory. He went on and worked looking at the messenger graph that has hundreds of millions of nodes and billions of interactions, and just did some really nice work that will be discussed at World Wide Web and elsewhere on those results. So Yuri has been tremendously productive and energetic over the course of his 4 years at CMU. And you'll see today just a sampling of the work that he's done bridging algorithms, sort of social network analysis, and really interesting innovative problem areas.
Okay, thanks. Okay, thanks everyone for coming. So let me start. What I want to start with is the web, right? If you think, what did the web give us? And at Microsoft, you know this, right? It gave us these large online systems, or call them computing applications, that have detailed records of human activity, right? So here are a few examples, right? We have online communities like Facebook or MySpace, where we have like 64 or 300 million users, where we know everything about them and about their social interactions. Then we also have like communication logs like Instant Messenger, where again it's hundreds of millions of people. Also, blogging and social media are popular, right? Again, we have detailed traces of how people blog. So the estimate is that there are 250 million blogs worldwide. Presidential candidates have blogs and so on. And the other thing, the other application that again we have detailed traces of human activity are these large multiplayer online games like World of Warcraft or Second Life. And these things that have like very rich internal economies where the GDP or the worth of that economy is like in billions of US dollars. And actually there are, I know in China there are factories that will where people play World of Warcraft and then they sell their new gadget on eBay and you can go buy it. Or there are websites where there is daily exchange rate between the Linden dollars for Second Life and real US dollars. So you can go buy and do the exchange. So
World of Warcraft, does it also have an internal currency? Or?
Yeah, they have an internal currency and you can trade and get things. And there are like stock exchanges inside.
And is the Linden dollar going up with respect to the
That's a good question. I haven't checked. But you get, I think, for $1 US, you get like 3 Linden dollars. So at least that side is good. Okay, so this is the motivation, right? So this gives us a lot of opportunity for impact, both in science and also like industrial, right? These are all applications that are running on computers. So that's why computer scientists are interested in them. And there's also a lot of, we have social interaction. So it's good to do, it's a bit more general than just that. Structures that I'll be talking about today are networks or graphs, so graphs as data. And here I have few examples. For example, World Wide Web, you can think of it as nodes are web pages and there are hyperlinks between them. Then internet, like autonomous systems. Again, we have autonomous systems as nodes and connections between them. Of course, online social networks like Facebook, MySpace, and so on. Again, people and social interactions between them. Communication, I think this is email. Again, how people send emails to each other. Citation networks are another example of a network where here this would be scientific papers and directed connections are now the references between them, biological networks and so on. So this is what I'll talk about today. And if you think interestingly, it is that networks have they share properties. And if you go and ask what do we know about the structure of such large networks, I would say we know a lot about their properties. So here I have a few buzzwords or names that catch attention, but it's no need to go through all of them. But like we know that they are scale-free, we know that they have small diameters, we know they have communities, we know they have network motifs and things like that, right? And then we also have a lot of models to think about think and reason about the properties that we find in such networks. And models are like preferential attachment and copying model, and so on, right? So we know a lot about the structure of these networks or network systems. What we know much less about are processes and dynamics of these networks. And this is exactly what I'll talk about today. So dynamics. And there are two aspects of dynamics. First aspect is network evolution, where we ask how does the network structure change as the graph evolves. And then the second question is, that's a different question, is diffusion and cascading behavior. So basically, how do things spread over the graph? And this is another aspect of dynamics. So to be able to work or to observe the emerging patterns that we are interested in, we need massive network data. And here I'm just showing you a few of the network data sets that I will also talk about later and run my experiments on. So the largest one that we worked on, and actually it's the largest one everyone ever worked on, is the MSN Instant Messenger network. So this is what we've done 2 summers ago here with Eric and Sue, where we have 240 million people, 30 billion conversations, 4.5 terabytes of compressed data. It's 255 billion exchange messages. So this is 1 month of all the whole Earth activity on Microsoft Instant Messenger. Then what I'll also show you is some study about how people recommend products to each other, where we had 4 million people and 16 million explicit product recommendations and data whether people accepted the product recommendations. And I also show some work on the Blogosphere, where again we have like 50 million posts and hundreds of millions of links. And the plan for the rest of the talk is to fill in these 4 boxes. Basically, we have 2 lines of research. One is on diffusion and cascading behavior. The other one is on network evolution. And first, we'll see some patterns and observations, so basically measurement on real data that will then motivate the second part of every of the 2 lines, where there will be some modeling work or some algorithmic contribution. So basically how to exploit what we see in real data to do something better. And I'll start with diffusion and cascading behavior. Right? So here is the idea. What should we be thinking about? So what I mean by diffusion or cascades are behaviors that cascade from node to node like an epidemic. So one can think of like news or rumors or opinions, how they propagate through the social network. Similar thing is word of mouth, where people recommend products and you hear from your friends what's a good thing, what's a hot gadget to buy. And also like infectious diseases like flu that propagates through social contact. And right as these activations spread over the network, they leave a trace. And we call this trace a cascade. So what I mean by that is that if we have a network and then some node gets infected and then their neighbors get infected and this spreads through the network, then the propagation graph that gets created is called a cascade, right? So there was an infection that spread through the network in this way, and this we call a cascade, okay? And what I'm interested in is how are these structures? And you can go and observe these structures in two settings. The first setting I'll show you results on is this viral marketing setting, where we have people make and receive product recommendations and purchase products. So the way you can think about this is basically this is data from some large anonymous online retailer, right? Where people come, they make a purchase. At the time of the purchase, they can make recommendations to a set of other people, basically by typing in their email addresses. These people receive recommendations. If they go and click on a link that they received in the email, make a purchase, they get 10% discount. And the person who made a successful recommendation gets 10% credit. So it's a incentivized viral marketing scheme, right? And this behavior then, okay, leads to happiness and further propagation of recommendations, okay? And here we had lots of data. So basically 4 million people, 60 million recommendations, and 500,000 products.
Are you allowed to tell us what the business is?
No, sorry. If we shut down the cameras, then yes. But basically, think of it as one of the large online retailers. Think of it as Amazon or whatever, okay? Something like that. Okay, so this is the data. It's basically DVDs, music, books, and videos. And then the second case that's very similar is the blogosphere, right? Here we have bloggers writing blogs, and they can refer to other pieces of information on the web through hyperlinks, right? So I have a set of blogs. Some blog writes a post, and then Azure decides to cite it, and this way the whole information propagates, right? From the source blog through other blogs. And then, of course, another piece of information can happen, and again, the whole thing propagates through the blogosphere. And again, as it propagates, it leaves a trace, right, a cascade. So this is a second case that we are interested in. And here we had 1 year worth of data for like top 50,000 blogs that generated 10 million posts and 16 million links between these posts. And if you now, the first question you can ask is, how do these cascades or propagation graphs, how do they look like? Like, can I draw them and just topologically enumerate them, right? And the question is how rich structures they are. Are they more like chains, which would mean very long and thin, or they are like stars that would be like just bursts of activity, and so on. So here is the first result. This is for the blogosphere, where I'm showing you the top graphs ordered by frequency, and the information propagates top down, right? So the direction of the link is the direction of the hyperlink, okay? And what you can see is that they are very sort of non-interesting in some sense, right? You have a lot of these stars or tree-like patterns, right? While if you do the same for viral marketing, these are the DVD recommendations, they look a bit different. And again, what I'm plotting you is cascades ordered by the decreasing frequency, right? So here, what we had to do to obtain this was basically develop a very quick or a heuristic adaptive algorithm for graph isomorphism testing, right? Because for every graph, you want to count what's its frequency.
So
yeah?
are none of these subgraphs of the other one?
They can be. So here I only took the full cascades. So I'm not doing really the subgraphs, but I just take the full cascades and count those. Okay? But still, what you can see is, yeah, the bigger the graph, sort of the smaller the frequency, but then you have things like this that are very different, right? And just to say what are the differences between both cascades.
Why do you need quick heuristics? I mean, on graphs of 4 node vertices, I can just do it by hand.
Because I did it very far away, right? I did it for everything. Sure, what I do is like up to size 8, you can do it exhaustively, so the results are correct. But then, sort of, the larger the graph, the less good is your heuristic, basically. Okay, so that's how I did it. Basically, the two conclusions. In information cascades, you have less collisions or less summarizers, while and also the DVD recommendations are more social, right? You have these richer structures where people recommend to same sets of friends, like here and so on. Also, you get less chains as in information cascades. So this is also sort of at the high level, what are the differences?
So did you have the data to see when the next recommendation comes in whether it's the same people?
I had the data, yeah. I don't know I can give you a quick answer on that.
So you didn't really look at it too?
I didn't look at the individuals level. I looked at it just like at the aggregate level of topological features, or basically what kind of subgraphs are created.
For example, there's always, because the marketer would obviously be interested if there are always these 5 guys and they
Oh, but you're going to look at
Let me show you
right?
next slide. Okay, so what is a very natural question to ask then is once you say, okay, I know what happens, you can ask, how does your this is what marketers would ask, right? What's the probability of adoption given the number of your friends who already adopted, right? And of course, the shape of this curve would have many consequences for algorithms and models. And there are two different ways, or two very competing hypotheses. One would be these diminishing returns, right? I'm plotting the number of your friends who already own the product or own an iPod, and that's your probability that you go and buy an iPod, right? And the idea is that, you know, the more of your friends that own it, the more likely you are, but this probability is increases slower and slower, right? You have this diminishing returns type of behavior. The other also very plausible hypothesis would be to have a critical mass or a thresholding behavior, where the idea is that your probability of buying is very small, but when a critical number of your friends buys the product, you go and buy it immediately.
And it's the number, not the proportion of your friends?
Um,
So people
here-
with few friends are just as influenced by a few people as people with many friends?
So I'm doing it as the number of friends you have. You could also do it as the proportion, but then it would be very biased because in networks, right, the degree distributions are very skewed. So it would be very, very biased. Okay, so I think this is a better way to do it. So it's the number of your friends that bought it. Okay, and to answer this, we need lots of data, and I'll show you the result basically. So we took all the DVD recommendations, that's 8.2 million observations, and I'm plotting exactly what I was plotting before, right? So here is the number of recommendations you receive, and here's your probability of purchasing, right? And what you can see is that you have this nice diminishing returns property, and actually that saturates quite quickly, and then remains constant or whatever. What you can also see is that we needed 8.2 million measurements to obtain this curve, and even here, like, our error bars get quite large as we get above 10, 15 recommendations. Interestingly enough, same type of diminishing returns behavior also happens for example, for group membership. Basically, what's your probability of joining a group given the number of your friends that are already members of the group? This was by Backstrom and al. And then also for probability of communication, basically. What's the probability of you sending an email given the number of common friends you have with that person? And again, you have very similar diminishing returns behavior. So this...
Now, these aren't things that have some kind of a network effect themselves, like the Zune, if people were actually sending things back and forth, where you would have a network effect so that if a critical mass of your friends owned it, it would start to be of value to you. This is more just like...
So you can think of this, they may be individually, there could be like these critical mass effects, but if you put enough of them together, or if you measure the population, that's how the population looks. So a priori, this is how it looks. But then maybe you could find an individual product that could really, okay, so this is sort of the aggregate type of analysis. Okay, and all I want to do here is to say, remember this diminishing returns curve, because we'll need it later also.
And did you see the same curve for the variety of products that you looked at, the DVDs and
we, for example, for books, so these are DVDs for books, we found that actually it went down. So it was like you stopped paying attention very quickly, and you sort of built resistance against the products. So it depends.
Maybe your friends lent it.
Maybe, or actually we have like models that predict how well, that will tell you how well will the product be recommended if you get recommendations.
Mass, kind of the
No,
it was always diminishing.
It was always diminishing. We never saw something going up. Either it was diminishing or very quickly and then going down. Okay. So so what I showed you now is basically diffusion and cascades. What are the shapes? What is the human adoption curve? And now I want to use basically these findings to design algorithms to find influential nodes in networks and to quickly detect epidemics. So here is what I want to talk about, is basically how to detect cascades and outbreaks in networks. And the same question makes sense in multiple domains. So for example, for information epidemics, I can ask, what are the most influential blogs? Or what are basically which blogs should you read to be most up to date, right? That's the question on the blogosphere. For viral marketing, you can ask, who are the trendsetters? Who are the influential people? And in disease spreading or virus spreading, you can ask, where could I put my monitoring stations to detect these epidemics as quickly as possible? Okay, these are all different flavors of the same question. And what I mean by detecting cascade or epidemics is the following. So if I have a network and a particular node gets infected, then this infection spreads through the network. And of course, another node can get infected, and the infection would spread in a different way. So the question is, where do I place my monitoring station, or which blog do I read, so that when there is a story or an information cascade starts going on, I get to know about it as quickly as possible. Okay? And there are two aspects to the problem. So first one is, what's the cost, right? Cost of reading a blog or monitoring a node can be different. Okay, so there is a cost assigned to every of the nodes. And then the other aspect is, what's the reward? Okay, and there are many kinds of rewards we considered, and one that's sort of the easiest to explain is you want to minimize the number of affected nodes, right? So the idea is that if you have a set of nodes that you are monitoring, so okay, you have your cascade. Now you decide that you'll monitor 2 nodes. So your reward that you get is basically the number of nodes that you save from infection. So here the idea would be you raise an alarm, and this is the set of nodes you save. Or on the blogosphere, the case would be that if the story starts here, you want to be the first to know, right? You want a lot of people to know after you know about something. Yeah?
So this would seem to depend on the trials. Some places much more likely to stop the disease than others. Like,
sure.
And also some blogs may be much more influential.
Sure.
So did you model that too?
I don't really need to model it because that's the data I'm using. I'll come to that in the next slide. Okay. So this is the one objective functions. There are other objective functions that also make sense. For example, you would want to minimize the time to detection, which means you'd want to minimize the time that went from the introduction to when you detect. Right. This is time in days or seconds. And also, for example, one would be that you just want to say, oh, I just want to maximize the number of detected outbreaks. I don't care how late I detect it. I just want to know, oh, there was an outbreak. Okay. So these are we have cost and we have an objective function. And now basically more formally what we are solving, right? We have some graph and the budget, and we have data on how cascades spread, right? So I have k cascades, and basically this now here I have no restriction where this cascade started, right? So basically if someone produces more cascades or larger cascades, that will be reflected here. Okay? And what is my task is to maximize the expected reward, right? So select a set of nodes so that select a set of nodes A, right? That my expected reward, right? The reward for detecting a cascade will be maximized subject to the cost. And doing this precisely is empty hard, right? It's a max cover type problem. Yep.
I'm sorry, where did probability come from? Excuse me, probability.
Oh, prob of I, you can think of, it's a probability of a cascade. You can think of it as a weight, or you can just forget about it. So it's another thing that you can sort of weight your cascade by probability of occurrence. So this is, going back to the question, this is another place where you could say, oh, these types of outbreaks are more probable than the others. It's just a weight, or it can be 1 or whatever. Doesn't really matter.
It's actually part of your input.
It's part of my input, exactly. This is part of the input, and I don't really care how this is set. As long as it's non-zero, it makes sense, okay? So this is the problem, and this is what I want to tell you for the rest of the few things. Basically, I want to show you the property that we'll exploit called submodularity, and then I want to show you the algorithm how to exploit the submodularity, and then I want to show you how to speed up the algorithm. So
it's empty for KE with the submodularity.
Sure.
It is.
So why do I want to talk about submodularity is because there are nice results about it. So let's consider the greedy algorithm, right? Where the idea is that if I have my network and these are my rewards I get from my sensors, the idea is that I consider all possible sensor placement and I pick the one that has the highest reward, right? And now I sort of decide on this one. My rewards get invalidated now, and again I recalculate what's the benefit of placing sensor C to already what I have chosen before. I pick the best one and place it, right? And there are 2 observations here. So one is that this will be slow, right? Every time I have to go through, consider all possible placements and pick the best one.
Are you just doing it one sensor placement or multiple sensor placement?
I'm doing multiple. Just say, for now, think of somebody tells me I want to place K sensors, right? So for everyone, I pick the best one, decide on it, reevaluate everything else, find the best one, place it, and so on.
Also, I don't understand how to get the cascades. Like, they are learned?
They are from somewhere, right? So that's the input. For example, for the blogosphere, I can trace them. I'll show you but basically the idea is that somebody tells me how things spread. So basically what is my input is a set of triples, cascade ID, node ID, and time when that cascade hit that node.
So it's sort of in hindsight, right? I mean, we sort of look at the thing and said, if I had put sensors, when would I have?
Exactly.
So in that sense, there's no learning involved.
There's no learning, exactly. There's no modeling. Everything is input. It's just the optimization part. And actually for blogs, I can talk about that. In blogs, you would want to generalize into the future, right? You'd want to say, if I decide on reading /dot today, I would want to capture something that will happen tomorrow. So it's a bit different. Okay, but let's go on. So okay, I have the greedy algorithm, and then there is a nice theorem that I'll show here is if my objective function, the reward I'm trying to optimize, is submodular, you can think of it sort of as like a combinatorial convexity in some sense, right? If I have this diminishing returns property, then there is this well-known theorem that says that this type of algorithm will be near optimal, right? At worst, it will be at 63% of optimal solution, okay? Sure, you can call, yeah. Either way, right? So what do I need to show you, right? I need to show you that my reward function is monotone, and that's sort of obvious because monitoring more nodes will never hurt, right? Placing more sensors in the network will never decrease my reward, right?
There's the cost associated with placing.
Sure, forget about the cost, right? So it's, just put it. You can say, you know, the more you add, the higher the reward, right? Here I'm just talking about the rewards. I don't really worry about the cost yet.
Well, I think what you're saying is you have a certain budget and you can spend all the budget. You don't care, you don't try to save any of the money in the budget. So you aren't trading off how many sensors to put out there versus the reward. It's just you get 10 sensors and
No, he might get 11 because he chooses cheaper nodes.
well, I mean, you can do
But
that.
I'm not
But
really
he's
talking,
using
I'm
up
not
his
there
But
budget.
you
is
always
what
use
you're
the whole
saying.
budget.
I'm not there yet, actually. For now, just let's assume you have infinite budget. And I'll come to the budget case. Okay, so this is first. It's monotone, right? The more you place, it doesn't hurt. Now you want to show it's a modular, and what submodular means is basically that if you have some solution and you decide to add a sensor to it, then the marginal reward you'll get for this will be higher than for another placement that is a superset of it, right? Sort of, it says that the more you add, the smaller your marginal gains will be, right? The diminishing returns type of curve we had before, okay? Yeah, and here's, to illustrate this further, there's a very natural example of a submodular function. What you can do is consider some sets, right? Here we have like the 3 sets, and the reward we are getting is the size of the union, okay? So basically the size, the covered area. And so this is my set of sets. Now I consider adding another set U, right? I'm on that side. So now the marginal reward I'm getting is this area, okay? And now if I consider a superset, so some other set of sets B, that's a superset of A, and I consider adding the same thing, the same element U to it, the same set, now the reward I'm getting is smaller, okay? And that's exactly the submodularity. So this is what we know about them. And the other thing that we know is that if we combine them, right, if I have some non-zero value times the reward, this will remain submodular if Ri is submodular. And if you think, basically what you can show is that our reward functions are submodular, and the one that I'm focusing on is exactly like that, right? So I have a cascade. I have a reward that says what is the set of nodes that I save from UK, right? So if I would place a sensor here, then this is a set of nodes I save. If I would place the sensor here, this is a set of nodes I save, right? So now my Ri, so reward for detecting cascade I by monitoring nodes A, is just the size of the union, right? Which by the argument in previous slide is submodular. And then my global optimization problem is just a combination of these rewards that I get for each individual cascade.
So the theorem on the previous slide, you don't have to go back, but was it positive combinations of submodular functions?
Yeah, non-zero,
Or,
exactly.
oh, okay.
Okay,
So it doesn't have to be a
probabilities.
complex,
Yeah.
combination.
Just some non-zero values.
I'm getting confused about what was proved by whom, and I want to ask Sebastian, what did you and Elchanan prove about this?
We looked at the viral marketing problem. I'm sure you know about this, the
Okay.
Klein-Bird model, where it's a specific model of how influence propagates in a network, and we showed that indeed you have this sort of global submodularity property.
And how does that compare to this?
It's very closely related to this. I don't know if you know.
Submodularity of what, though, in your case?
Hmm?
Submodularity of what?
The submodularity of the number of people that get infected with the.
Sure, that is very similar, right? There you are assuming the model, and then you can generate the randomness in advance, and you are getting the same type of sets, right? Here I'm using this as data, and sure, what I'm showing you is just the set cover. So the other objective functions that are there, they don't reduce to set cover.
Because I understand what he's doing in terms of placing sensors, and he has a reward function. He's trying to optimize the number of nodes covered or blocked. And I'm not
As
sure
part
what
of
we're
marketing
doing.
problem, you want to maximize the number of people who are
Exactly.
affected.
Right.
Okay.
So they are
So
doing
That
the
was
minus
a
of what
consideration
we
as
are doing.
defined for Tardosh in the KKT paper. That was-
So the KKT paper is a subset of this. Basically,
And
what?
it proves
yeah?
the conjecture in the KKT paper.
Okay.
But that doesn't include this because this is kind of coming from the other direction.
Exactly. This is coming from the other side. Okay. So this is just the simple thing. And what we really did, and I won't have time to tell you, is basically we extended this setting that I just showed you to the case where you have costs, right? And the algorithm for which you can prove bounds goes the following. Basically, you do two independent runs of a greedy algorithm, right? In the first one, you just ignore the cost, you greedily optimize the reward and cut once you exhaust the budget, okay? And then in the second run, what you do is, again, greedily optimize the reward cost ratio. So this is sort of how much money do you get for the buck, or how you say, right? How much do you get? This is the reward you get for sensor, and this is how much it costs. And the higher this ratio, sort of the better the sensor. So if you do this, then independently do this and pick the best of two placement or solutions, then you can show that this is near optimal, meaning you lose 1/2. So it's 1/2, 1 minus 1 over e.
You wouldn't need this term.
That's true.
Okay. So this is basically, you actually assume you have a heterogeneous cost.
Exactly, you have
Okay.
heterogeneous costs. So that are non-uniform and each node has assigned a cost. Then you can prove this. This is still too slow. So these two independent runs of greedy are still too slow. So what we also do is use this idea of lazy evaluation, where the idea is that basically what submodularity gives you is that the marginal rewards will only decrease as you place more sensors. Okay? So you can, what I mean by that is, the whole rectangle is at the first where no sensors are placed. Now if I place sensor A and ask how much reward do I get from adding D now, my reward only shrinks, right? And if I would go and place another sensor, let's say B, and ask how much do I get now from D, it gets even smaller, right? And you can use this as an upper bound when you are placing sensors. So I just quickly showed the animation. The idea is that again, I evaluate every sensor, pick the highest one and place it. But what I do now is I reorder this by the reward I got in the previous case. I go reevaluate it because it's smaller. This is my current reward and this is the estimate, right? I move it down. I retry B now, and now I can stop, right? And the reason I can stop is because I know the reward for E will only get smaller, so I know this is already the highest guy. So, and if my data cooperates this way, I can save a lot of time because I don't really need to go and check all the sensors. So that's basically the idea.
So you can't prove anything for that.
Of course, yeah. You can't prove. So you can still if the data is very ugly, then I'm still doing the same
Sure,
work.
because you could set it up to
Exactly,
get
the
that
last
balance.
one would.
Right.
Exactly. Okay, so what I want to show here is now the results for this blog case, where the question is which blogs should you read to be most up to date. So the number of blogs you select, here's your reward, higher is better. Here is our reward, and these are rewards if you would be using some other heuristic placement. So for example, number of inlinks is used by Technorati today that says who are the most important or influential blogs. And basically what this says is if you read the Technorati blogs, then you do much worse than what you'd do, or you know much less than what you'd do if you'd be reading the blogs we suggest. Okay, and there's a website we have with all this.
Did you use a cost function for that?
Here the cost function, here I was using unit cost. So what you can also do, you can use, so we were using cost where the cost was the number of posts on the blog. So the idea was, you have 10 minutes, reading each post takes you 30 seconds, what's the optimal? And there what it happens actually is you start to overfit, right? Because you are training, your sort of placement now is sort of training in some sense, right? You decide on historical data, but what you really want to do is perform well in the future. So you are sort of overfitting over the small blogs. And we have results there, and I can talk more offline later. Okay, so this is first. And
so these results are on a holdout set, or are they?
These are on the training. These are on the training set.
This is on the training set.
This is on the training set. So yeah, just the speed ups, exhaustive search. This would be so again number of blocks selected, running time, exhaustive search, basically all possible placements. a greedy algorithm goes like quadratically, and then our algorithm, which in this case is like 700 times faster. And then basically the same thing applies to water sensor networks, where the idea is, right, you have this water distribution network, water flowing around. The question is, where do you place your sensors to detect these epidemics as quickly as possible? This is, again, similar type of how many sensors you place, what's the population you save. We do much better. There was a competition, and we were better than everyone else. But in a month, Andreas, who's also a co-author, I think will give a talk on much more about sensor placements and things like that. So that's very quickly. So to recap, I'm a bit behind. So basically, diffusion and cascades, this is what I showed you. Now I quickly want to show you this network evolution part. How does the structure change as the networks grow? And first I want to give some background. Where the idea is that you have some empirical sort of how this work all goes, right? We have some empirical findings that then lead to new network models. So here's an example, right? If we found that real networks are scale-free, which means that they have power law degree distributions, which means if I plot log degree versus log probability of seeing a node with that degree, that follows a power law, or on log-log scales, that's a line. Okay, so then we said, okay, what's a good model? For example, preferential attachment that basically tells me when a new node comes, how it will create its edges to connect to the network, that sort of this mechanism of node attachment would give me this global property of the network, right? And this way we say that we get the explanation in that way, okay? Such models, right, make many assumptions, and you can also use them to make predictions how other network properties will behave, okay? And what I'll show you is what has been said about how do networks evolve. How does the structure change as networks evolve or grow? So there are two such questions that I'll investigate. First one is very simple. What's the relation between the number of nodes and the number of edges in the network? And prior work assumed that it's constant over time. So the average degree is constant over time. But it turns out if you go and look at the data, it's not really constant. It's increasing. So what I'm showing here is number of nodes at particular time versus number of edges at particular time, and I'm plotting this on log-log scales. This is for internet autonomous systems. It's like 700 different graphs, one for each day of the year for 2 years. And these are physics citations that go from 1993 till 2004. So it's like 10 years of academic citations in physics. And what you can see first is that this is getting denser over time. And the reason how you can see this is because it's not this relation holds. Basically, it says that the number of nodes at number of edges at particular time is proportional to the number of nodes to some power, right? If now my power would be 1, then I'm in constant average degree setting, while if my power is 2, then I'm like generating a click, right? Everyone is connected to a constant fraction of all the nodes in the network. So now if you look what is...
So if you look at the internet, it has a very... I mean, the power laws in the internet are sort of a little dubious, and they're in particular really bad at the upper end, right? I mean, they don't fall off the way people predicted. So what if you, so does the densification come from that? In other words, does it come from the fact that the router doesn't have more than X outlinks or some sort of truncation of the degrees, or does it really come, even if you would integrate only the beginning where the power law is really nicely powered, or you still have this densification?
So for autonomous systems, now it's like accepted that they, like everyone in that community believes that they are densifying. That's my understanding from, and I saw people citing basically our work that is going on. What you can also do, and I think what you are asking is the relation between degree distribution and densification, right? And there are two things that you can show. One is if your degree distribution has an exponent less than 2, right? Then you will be densifying because less than 2 has infinite mean, right? So that will, that is, so you can say my degree distribution remains constant over time, but it's densifying because of the number of samples is increasing. The other thing that you can say is, right, my degree exponent needs to get shallower, sort of my tail needs to get fatter.
Otherwise it's not it.
Exactly, and that also you can find data. So I found data where one was the true, and I found data where the other one was true, where sort of the degree distribution was power law, but it was slowly like shifting. So both are happening.
So for the internet, which one is happening?
I can't give you the answer. I would need to check the paper. I forgot.
So when are we going to reach a bibliography event horizon where all of our papers are purely citations?
I mean, what this is saying, right, is that your citation lists are getting longer.
That's what I mean. So eventually all our papers will just be citations.
Hopefully not, right?
There's a natural cutoff from review.
So we are really running late. Should I like skip something? Should I just run through, or
Till late, don't worry about it.
so I can just go?
Keep going.
Okay, because I'm.
We have an hour and a half because people might start talking, like Jennifer's talking to you about.
Oh, okay, so that's no problem because I'm really like trying.
You started late and we're asking lots of questions.
Okay, that's good.
Eric said we plan an hour talk and then we harass you for half an hour.
Okay, that's good. So.
Well, but we do it interspersed.
Sure, and if you have to go, please leave. Okay, so I won't be offended. Okay, so this is the first thing, and then the other thing is how do the distances, how does the diameter of this network change, right? And people, or what if you use the models people developed before, then you can show that like diameter will be like very slowly increasing, like log n or log n. So very slowly, where n is the number of nodes. And this is intuitively makes sense, right? If you take something that has size n and you ask what's the diameter, this is the diameter, right? And if you take something bigger, the diameter of the thing is bigger, right? And as you might have expected, I'll draw a cross over it, and here is what's going on, right? So this is same autonomous systems, size of the graph, versus here I'm plotting effective diameter, which is like the 90th percentile of the distribution of the path length. So it's sort of smoothed out version of the real diameter. And you can see it's slowly decreasing. And now if you look at the citation network, same one as before, here the behavior is much more dramatic, right? So I go from 1992 till 2004, and my diameter shrinked from like...
And you're looking at the largest connected component.
Exactly, yeah. Or actually here I'm not really, because the way I do the effect, the way I define the diameter is like the total number of, so what is the value at, or what is the number of hops within which 90% of all reachable pairs of nodes are reachable, right? So I'm sort of working with reachable pairs of nodes instead
but
of.
Only reachable, yes. Okay.
Exactly.
That's what I'm saying by a connected component. Obviously.
I don't really need to worry about connected components, right? There is, because I just worry about the number of pairs. So it can be, graph can be disconnected and the definitions still work.
How does this look if you try smoothing it? What if you look at the 99th percentile? I mean, is it still so dramatic?
Here, yeah. Here it's hard to say. If you would be, for example, taking 99, or if you would take the maximum, here it would be constant, while here it still goes down. Okay, so basically the story, diameter shrinks over time as the network grows, right? Your network gets larger and larger over time, but the distances shrink. And then a very classic story, right? None of the existing models work, so you need a model. And the idea that I want to show you is this, how to generate graphs recursively. And why would you want to generate graphs recursively is because usually recursion or self-similarity fractals is connected with, or gives rise to skew distributions like power laws. And we see lots of power laws in the real graphs. So that's the intuition part. And now I can show you what's the model. So here we call them Kronecker graphs, and here's the idea. You start with some initiator. So here's the graph. This is the corresponding adjacency matrix. And what I'll do now is I'll recursively expand this matrix, and I'll expand it in the following way, that in every cell of my 3x3 matrix, I'll stick in the full matrix and multiply with the constant there, right? So here I have 0 times the whole matrix is a block of zeros, and this is now 1 times the whole matrix is just the whole matrix, okay? And if I continue doing this, then I arrive to these nice self-similar matrices, right? That have this nice recursive structure. So here you can see zeros corresponds to that corner there, and then again every little piece again has the same structure, right? So what I'm doing, basically I'm doing the Kronecker product or a tensor product over graph adjacency matrices, and this is just the way how do I generate it, but there's also a nice sort of social interpretation or intuition why this could be really going on. But here I'm just, which is if every node has a set of attributes, and then this tells you the probability of 2 attributes, or the probability that 2 nodes link given the attribute. So this can now encode the probabilities that you form a link given that you share an attribute or not. Okay, and then yeah, that's all I want to say. But I can explain more.
Say that the smaller communities would do the same thing on a larger scale.
Sure, or you could
so
think
the
that for every
communities would share
attribute, right here you have a 3-value attribute. You could say for every attribute I have a attribute similarity matrix that says, you know, you like ice cream, you don't like ice cream, you don't care about liking ice cream. And then you say, okay, you write the 3 values here, 3 values there, what's your probability of connection? Okay, so that's how you can think about it.
As the network grows, you care about more and more attributes.
That's exactly what's going on then, right? As you are expanding it, you're sort of adding more and more attributes to it, to every node.
But why would you be recursively generating on the same, why would you have the same matrix? I mean, so you add more and more attributes, but why, when I look at a sub-attribute, would I expect to find the same distribution of likes and dislikes? I mean, the same
Not necessarily.
matrix.
That's a good point, right? You could have a different. So instead of taking this one and powering it, you could take every time a different one. Exactly, you can do that.
And that makes a little more sense in terms
Of
of
attributes.
social interpretation and attribute.
I totally agree.
But you'd still get a non-trivial fractal dimension.
Exactly. So what you can do, so if this on the top is the graph generator model you assume, then you can prove that this will have a lot of properties, so we give you graphs that have similar properties than real graphs, right? You can prove power law degree distribution, you can prove densification, shrinking or stabilizing diameter, you can prove some spectral properties. So this is what you can do with this model. And what I want to show you next, so now we have a model, we would like to fit it to the data. So basically we would like to generate realistic synthetic networks, yeah?
Can you generate arbitrary degree distribution?
No.
Okay, fixed.
It has to be a multinomial. So basically, degree distribution, you can prove it's multinomial. So now you can make it really skewed and it will look like power law, or you can make it different. But you can't generate, with Kroneckers, of course, you can't generate any graph you could think of. So sort of the model gives you the bias, and the bias seems to be the right kind of bias for real graphs. Okay? So
when you have power laws, how do the cutoffs go? Are they exponential or?
Yeah. So I can show you. I'll show you the results from the fitting, and you'll see how my degree distributions look. So they are sort of more log normal than straight power law lines because it's a multinomial. Okay. So what I want to do now is I want to generate realistic looking graphs. So here's the task, right? You give me a graph, and you say, okay, generate me a synthetic graph. That then if I go and measure some properties, these properties would match. So for example, if I go and measure the degree distribution matches. Or you'd say, okay, I want to measure the distribution of path lengths, and that matches. Okay? So that's the task. And you can ask, why would you want that, right? There are many scenarios that you'd want this. So for example, for anomaly detection, for like simulations, if you say, okay, I have my algorithm on the graph of internet today, and I would like to know how it will run tomorrow. So you need to be able to generate a synthetic graph that looks similar.
There's no great way to compare arbitrary graphs besides doing these simple properties, right?
Yeah, I mean,
Yes, if there was.
I don't know of a better way than sort of measuring these types of things. You could, yeah, I don't know of any good distance between graphs.
We actually
Yeah.
have a theory of that with Loxy-Lodas and a few other people.
What do you call that theory? Graph similarity.
No, we get limits of graphs, or graph limits, and then we have various properties that we compare in the limit.
Sets.
I can show you what I'm doing, and I think
what you do if you have graphs of different sizes, you take the adjacency matrix, you make it into a function by making it sort of by having sort of blocks, right? So think of the adjacency matrix, now draw ones and zeros into little blocks of that size. Now if you have two graphs of different size, you can sort of, they're normalized to be the same, but you still have to do isomorphisms.
Ooh, okay.
So which turn into measure preserving maps on this interval 0, 1.
Okay.
And then if these two functions now look similar, then the graph.
So
and
you're
we can
basically
show that
making your adjacency matrix smooth. Basically, you're making continuous approximation.
And we can show that about 6 or 7 different kinds of notions of similarity coincide when you do that.
Okay.
You know, we looked at spectral things, we looked at summative partitions.
So in particular, the degree distributions will be similar if they're
Right.
similar in this sense. So it's stronger than degree distributions.
So, and that's exactly what we were trying to do when we came up with this theory. How do we compare to
Okay.
I mean, the reason I asked those is because I don't have a good intuition about how wildly different graphs with the same approximate degree distribution should be.
So
They can
I'll
be
show you.
extremely
I'm not really doing this, so I'll show you what I'm really doing. Okay. So a natural. Sorry.
I said you could have saved me all my questions if you just told me this ahead of time.
So here what such an approach really leads to is asking, what do I really care about? Do I care about degree distributions? Do I care about diameters? How do I combine those, right? And what we do is we say, let's not commit, and we basically just try to match the adjacency matrices. So here's what we are trying to do. What sort of, right? So I will be doing maximum likelihood estimation. So the idea is my theta is now my initiator that has some values. I will use this to make I'll Kronecker expand it to get the real matrix. So now you give me a real graph, and I want to measure, you can think of this, how similar these two guys are, right? Or what I want to.
have to do isomorphism.
Of course, this comes here. So the idea is that I'm asking basically what's the probability that this thing would generate me this thing, okay? And as Jennifer said, this will be very expensive, right? N factorial is sort of for isomorphism, okay? Exactly, right? You have this n factorial different labelings because, right, if I permute this matrix this way, it's a different graph, right? Or, these two could be the same, this one, but this one would be just the permutation. So you sort of need to go over all possible permutations. What you can do is you can use metropolis sampling over the space of 4 permutations to do this in linear time, basically in constant time. Okay, so you don't really need to pay this factor. And then the other thing that will also happen is you still have this n squared term that's still too expensive for us. And why do you have n squared is because even if you know the permutation, now you have to go and traverse the full adjacency matrix and basically count how many edges do you hit and how many you miss. Okay, so this is, one is you need to decide on the ordering, and the other one is you need to traverse the whole thing. What is basically our solution here is that you can exploit the sparsity and the structure of Kronecker product, that you don't really need to go over the whole thing, and basically you only need to go over the edges, so you get ordery thing, right? And once I'm able to approximate this, basically calculate this matrix, now I just go do a stochastic gradient descent over my parameters, and this is how I feed the model, right? So the good news is that I can estimate the model parameters in order E time, right? In time linear in the number of edges. Yeah?
Technical question. Do you mix together stochastic descent with Metropolis resampling, or you sort of run Metropolis for a while, do a step and thing, and run Metropolis for a while?
The way I'm doing it, I do a step in Metropolis, reevaluate my gradient, and then I'm sort of averaging the gradients.
Okay, so but were you doing sort of momentum or online gradient descent where you're just always, every time you take Metropolis, you're slightly adjusting your things?
No, I would take my Metropolis for a while. I would get my gradients, average the gradients, do the step. That's how I chose to do it. I could also do it the way, basically, that after every step I make a small move. What I'm doing is I'm doing it in a batch right now. Okay, so I can do this in all time linear in the number of edges, and that's I can show you some results, right? So if I take a graph that's not too big for what I like to work with, that's 75,000 nodes and 500,000 edges. If you ask what's the space of all permutation, that's 10 to the million. But we can do that in 2 hours, right? So in 2 hours, I can find the parameters, and here they are. And now if I take my Kronecker graph generated from those parameters and my real thing and measure statistics, then this is how well I do. So for example, here is degree distribution, red is the real thing, green is our thing. You can do the path lengths. Basically, this is the cumulative distribution of the number of reachable pairs of nodes inside some number of hops. Again, we match that. You can ask what's the distribution of values of the first singular vector, and again, we match that quite well, right? So basically, through matching the adjacency matrix, we also match these statistical properties. Yeah.
It's amazing that you match with so few parameters to start with. So what happens if you increase the size of the thing?
I only get better. So, and then of course the question is, what is the size of theta I should pick? And basically what you can do then is you can use BIC, because it turns out that this, right, Kronecker graphs like define your distribution over graphs, right? And that distribution is like a, how do they say, curved exponential family. Yeah. So you are trading off the fit of your model and the complexity, the number of free parameters that your model has, okay? And you'd like to have the simplest model that fits well. So yeah, you can extend this, and it works nice. Actually, the other thing that I haven't told, but I can now also say is, right, the question is also, what are you converging to? And it turns out that even though like the optimization problem is non-convex, like just empirically, I was always able to recover the true parameters. So if I generated the Kronecker graph with some parameters, now I started from some random point and did gradient descent, I always converged the true parameters up to the permutation, right? Because if you permute rows and columns, you get different parameters. So it seems like your optimization space is like, has local minima, but local minima are global minima. And that's an empirical statement, what I'm saying now, okay? So this is the good news. Basically what I did, I showed you these things, and now I quickly want to show you two other things. Basically things that I've been working on here. One is about these web projection things. That's how do you predict the quality of web search results without even looking at the page content. And one are some cute experiments on the MSN Messenger. Right, so here's the scenario, right? Your user comes and types in a query into the search engine, and then search engine returns a set of results, right? Where now the red boxes are the results, links are hyperlinks, and then these red circles are just some other web pages on the web that make the whole result set connected. And now you can go and ask, is this a good set of a bad set of search results, where good means as evaluated by the human, right? You would show.
So how do you determine these extra nodes? Do you solve some standard
It's I do some approximation of the standard tree problem, exactly.
So you do as little as possible, as few as possible?
As few as possible. Okay, so the intuition we had was just, what are these connector nodes, we call them, right? How do you make your result set connected? You can ask the same question that is like, user again comes in, types in a query, you get a set of search results. Will a user reformulate this query or not, right? Will they be happy or not, right? And in a paper with Eric and Sue, basically, we were able to make predictions with 80% accuracy whether the result set is good or not. And so here I show two graphs, right? And one is good and one is bad. And you can try to guess and for yourself. So what do you think this is? That's good, and this is bad? Yeah. And that's exactly right, the intuition, right? So the intuition is, right, you come on the web, you have this web graph, and now the search engine is like teleporting you on the web graph, right? If it like randomly teleports you, then you are not happy. If it like teleports you on one single side, that's like a click, right, where everything's connected, you are not happy. But if it teleports you in a way that, you know, there is something connected, but also there's something around it, then you are happy with. And actually this comes out from the learning models we trained. Okay?
What about polyseming though?
Sorry?
What about polyseming? What happens if you have two big clumps that aren't very well connected, or they're connecting very tenuously? It still should be okay.
That might be okay. This just looks a lot like web spam.
Oh, well, that's just a scattered clump of bad.
Since we're learning how to model certain
But if you had, for example, something like the term jaguar is the classic one, right? You would expect to have two things,
clumps, right.
two clumps that are connected by a few Steiner
But I didn't
nodes.
know if
Connected by Sue's paper on the topic.
Yeah, I don't know. So, okay, so this, and then the second thing I want to show you is a small world experiment on the planetary scale, right? So there was this work by Milgram that you probably all are aware of, right? What he did was the small world experiment where people were asked to send letters from. So some people in Nebraska were asked to send letters to Boston, and they were able to send these letters only to their friends, right? And the question is, how many steps does it take for a person in Nebraska to send a letter to a stockbroker in Boston? And this is the data from Milgram's paper, right? 64 letters made it to the goal, and here I'm plotting the length of the chain versus the number of such chains, basically. What's the path length distribution, right? And what Milgram did is calculated the mean, and the mean was 6.2. So the conclusion was that 6 degrees of separation, right? People are 6 hops apart. What you can also do, the same experiment, you can do it with Microsoft Instant Messenger social network. That is right, you have this 240 million people with 30 billion conversations, and you can do the same thing, right? So now here's the distance in hops. This is the number of paths. Now I'm plotting on the log scale because my data is like 4 million times larger. But you can see, right, we get very similar. The mode is at 6, 7. But in contrast, we find these long paths. Actually, our average is 6.6, which sort of says it maybe should be called 7 degrees of separation. But basically, this is the finding.
Well, look, but your long path, I mean, it's exponentially decaying. It looks pretty linear
Sure.
there. So fine, you have sort of, if you have enough nodes, you always get long tails. But
I agree.
essentially, they're not there.
They are very small. Yeah, this is the majority.
Those guys are trying to reach in Tanzania from Christian's office.
Okay, so let me conclude now. I think I'm done. So basically, to recap what I showed you, right? I showed you that 2 lines of work, one on the diffusion, one on the networks. I showed you like empirical results on like cascade shapes, on human adoption curve, and on densification and shrinking diameters. And then I showed you this algorithm for placing sensors in networks to detect outbreaks. And I showed you how to model and how to fit models of graph generation. And I showed you, hopefully, that big data matters. And now I want to show you what I want to do next. And here I'm mentioning some companies, but all this data you have at Microsoft, so you can just forget about those. But basically, this is what I'm showing here is like a typical picture of how information propagates, or what is the holy grail of the web bloggers, right? The idea is that there is some obscure technological story rather than slowly propagates to mass media, right? And what we would like to do here is understand how does news and information propagate or spread, right? You could use these types of behavior to characterize or to suggest new ranking measures for blogs, right? Notions of influence. And what we also empirically found is that different categories or different topics of blogs have very different cascades. So you could use this to do some kind of sentiment analysis based on the cascade structure. And for example, what happens in this case is that if you look at Slashdot has cascades like stars, right? Slashdot says something, a lot of people get excited, but that's about it. While if you look at some more political blogs, right? Like I think this was from Michelle Malkin. Their cascades are sort of narrower but deeper, right? People, I don't know, start to argue, or they talk much more, they discuss things. So we just empirically see these differences. And the question would be, what types of cascades are there? How do you map blogs to cascades and vice versa? Okay, so this is first. And here I'm crawling a lot of blog posts to be able to do this. The other thing that you would want to do is have, right, so far I didn't even talk about how do you model information diffusion or propagation. So basically, ideally, you'd like to have a model where you say, what would happen with a particular piece of information on Slashdot if I put it there 5 minutes past 8 p.m. on Sunday, right? You know, will it create a cascade? How far will it go, and so on. The same is also then, if you have such models, then you can ask, where should I plant my information to get my effect? And why would you want to do that is to do like social media marketing. That's how they call it, basically, right? If you are a viral marketing person, or if you are a politician, you would want to know where to put your information to achieve the effect you want to achieve, okay? And then what this nicely leads to is basically how to handle richer classes of graphs, meaning what I was showing you till now is just the topology. But the question is, how do attributes on nodes and edges affect the topology? And what's the interplay here? So this is on the diffusion. On the network evolution part.
Can't you just put like weights on, so rather than having ones and zeros in your adjacency matrix, you would have weights on the...
It does already have weights.
Sure, you could have weights. What about text, right? For example, on blogs, you essentially have text, right? So that's...
Now, even when you do, when you did your cascades and you sort of put them into isomorphism class, That's a little artificial, right? Because in real life, the cascades actually came with timestamps, and so you would actually have a natural labeling of the edges. The first edge appears, the second edge appeared, and so on. And so that would tell you that structure you actually have. You just decided to throw it out.
For that case, actually, I agree. Okay, so but this I think nicely leads to the next question, or sort of the second line of future work that I want to do, is basically why are networks the way they are? Basically, models of network structure that explain why are we seeing things that we are seeing. And here we already have some very nice work on network community structure, and like also another thing that we have is like these models of microscopic network evolution, basically, where we had data, for example, for full LinkedIn network edge by edge. So right, instead of working with snapshots, now you know for every edge when it occurred. And now you can test likelihoods of various models, preferential attachments, and things like that. So this is one thing. The other thing that Facebook is very interested in is basically what's the health of the social network. That's how they are asking. But basically, the question here is, how do you steer the network to make it grow, behave organically? And more specifically, how is the adoption of Facebook applications propagating through the Facebook social network? So basically, this I'm working with the Facebook people, and the other thing that I think is very exciting is basically predicting the future, right? So modeling, predictive modeling of large communities, right? So what you can do is going back to the multiplayer online games, right? Like World of Warcraft, right? It's a closed world with very detailed history of social human activity. So what you could do now is use this to predict success of the guilds, basically alliances, who will win the battle, who will win the elections, and so on. And here I'm working with a company in Iceland. They have 250,000 people playing a space game on a single server. So it's a closed world of 250,000 people, and they have elections in June. So the idea is, can we predict who will win the elections there? And then another thing is basically scaling up, right? What I'm looking at is MapReduce type distributed architectures for large graphs. Here we already also have some results, and we have some active collaboration with Yahoo, but I could write Microsoft here, right? We have this 4,000 node Hadoop cluster that supposedly is like 50th fastest supercomputer, and we are trying to use this to do analysis of large graphs, right? Graphs that you can't fit into the memory. And just to conclude with something else, so this is how I see the whole thing, right? Networks and computer science. I think it's a very nice overlap of computer systems, machine learning, data mining, and sort of theory and algorithms. But even more, right? There are all these areas that all benefit from this, right? Statistics, computational biology, physics as complex systems, social sciences like social network analysis, and also there's a lot for interest from applications and industry. That concludes my talk. Thanks.
Lots of questions now, but it's a natural time for folks to step up, but we still have plenty of time for questions.
So I thought for a second all your closed things were going to form the MSN butterfly, but
no, I need to acknowledge all the people.
So throughout all your work, there's this basic closed world assumption of the network, right? And it affects more problems more or less. Like the MSN messenger, you'd expect that you're actually overestimating the length, since not everybody uses MSN messenger, of the true world's connection.
Sure.
Right? And it seems to affect more problems more or less. Have you given any thought in general to this closed world assumption, or even doing things like, say I want to detect when two people are communicating out of the network, and detect when people are communicating, so that I can say, look, there's a virtual link here and some other media dimension or something else.
So I agree with what you are saying in a sense that what we are doing is we are measuring this large amounts of data and hoping that this is real. I think the opposite scenario would be to go and study 5 people and see how well you can do there. And there's sort of this disconnect in some sense, right, between really understanding small sets of people. This is what traditionally social network analysis was doing. And then sort of this, they call it new kind of science or whatever, right, where you are studying emerging phenomena. I think the sweet spot is where these two views meet, and you could actually say something about individuals and the emerging properties of things. So I don't know. That's I think is the answer.
A question on the to get your reflection on what happens to a variety of the connectivity, diffusion, and evolution when it comes to powerful lenses onto the attentional lenses onto structures like Google or Live Search. You have a lens now that's doing its thing to reflect results and to inform people. Has a relatively small but powerful portal that can create all sorts of graph bending influences. So, what your reaction to that?
What's your question?
What you reflect on potential influence that on global structure of web, for example.
So how is
a small search engine might have? I mean, a search engine company, for example, like Google, onto the whole web.
I mean, sure, they are biasing it in some way, right? Just by results they are showing to you, right?
For the old blogs, how do I discover something on a blog? People don't always do RSS feeds on blogs. They might search on blogs, for example, to find something. And depending on how indexing is done, for example.
Sure, you will get different sets of blogs, so different blogs will get different amounts of exposure, and
I guess you might have very critical parameters changing their values even in the model of what the graph is like, potentially. But do you believe that the comments is so powerful that the lens effects of a search engine are small?
I think the world is so diverse, and there are so many different ways how to come to it that hopefully these effects would be small. No, don't agree?
I mean, how about spam? I mean, that's a lens effect too. I mean, that's kind of a backdoor lens effect, which we know throws everything off. Because the spammers know the lens that you use,
Not just
they
spammers,
change.
but people that want their pages to be shown up.
Sure, but right, and we do the same thing, and so we all change the structure of the web to conform to the lens that's being used.
Sure, for web search spam, that's true. On the other hand, we are trying to throw that away, right? So the question is, who is ahead of whom?
Is not there, right? When the web was early, I would put all kinds of links on my web page, which I don't put anymore because it's ridiculous, because everybody will just use the search engine instead of going to my web page to follow the links to something I have sort of discovered.
Sure,
Whereas in the old days, people would actually put them.
Sure,
I think there's a lot of research in which sense the search engines put themselves out of business by making it sort of less likely people put relevant links.
I agree with this.
Eric's question is really, can we adopt algorithms in such a way that they would be resistant to any sort of exploitation attempts? Because and sort of we should really study the algorithms.
It's sort of like the variant.
Yeah. And so we should study these algorithms under the assumption that there will be people who will be trying to exploit them and to actually see how resistant.
We've actually got work on that with John Hopcroft, who's upstairs, and some of us.
He should be here with upstairs.
Well, John said he either saw or will see your talk.
He'll see my talk
here. Right, so, because I said, I think you guys want to hire Yuri too, and he said, yeah, but now I've got to get this paper done. Well, the paper that we're working on is trying to understand ways of doing search. I mean, so what are some of the things we've done are variants of page rank that would be more spam resistant, that would weight down certain.
Exactly. I mean, right, ideally you'd like to, even like for algorithm design, right, you'd like to be able to say, if my graph follows a power law degree distribution, then I can do this well, right? That is kind of statements you'd like to do, right?
So most of the algorithms you talked about assume like that you know the underlying graph structure. Have you thought about problems where you see a lot of data, and then what can you tell about the graph structure from that? Like, for instance, like, you're seeing some network activity, but you don't really know deterministically the underlying graph structure.
Sure.
But like, what can you, like, what are the things you can say about the graph from that?
Meaning like doing link prediction and things.
Prediction, or maybe even the properties of the graphs, right?
So what I have working on, so I haven't worked on this problem specifically. What I have worked on is sort of how do you, how can you sample the graph to get to maintain your properties. The other thing is sort of the models I was showing, right? So also like Kronecker graphs. It would be, I think it wouldn't be too useful if you would want to use it to predict what's the probability that particular two nodes will create a link, right? While what you can use it for is to say, I want to generate something that looks realistic. If I step few steps back, it sort of looks okay on the aggregate. So this is what I was doing, and maybe not focusing on particular edges. But actually we have something like this that is coming up on how do you evolve your social network edge by edge? How do you like throw in individual edges? But I think what you are asking also comes up a lot in biology or sort of, or in even like a network internet measurement, right? Where you can measure flows between routers, and now the question is which router talks to which router, right? Sort of you can measure the flow between the endpoints, and there are ways to do that, yeah.
Like Paul was saying, I mean, you can always assume that you're observing every single link, so how do you take into account the secret?
Sure, so I think, sure, I can't assume that. On the other hand, I'm trying to take as much as I can to minimize this effect.
I have another question, I guess. The Kronecker graphs, they generate, you're just looking at the end result, right? It doesn't generate a series of network snapshots. So you're not actually, I mean, even though it's listed under network evolution, it's not an default. It's not a.
It is. It gives you a set of networks where the node set grows over time, and they densify, and you can prove the diameter will be constant, or the effective one.
Are you suggesting that is in some way really what's happening in the network evolution? I think is what she was asking, because you're measuring the end result and comparing it to known data. And
Sure.
do you think the way the web actually evolves is not that these things are happening simultaneously, but that there's some kind of recursive thing, that a community forms, and then within that you get a sub-community, and
There were actually works like early on that showed something like this, right? They were taking like sets of web pages on a particular topic and compare that graph with the full web graph, and they found some similarities.
Now, in fact, to make it more realistic, I mean, you were saying to me, yeah, you could Kronecker with a different one each time, but you're still saying, like in your 9 blocks, that you use the same subblock on every one,
Sure.
whereas in a realistic community, you would be using different ones on each block.
There's
and I'm
rewiring
trying
going
to
on.
figure out, just thinking about it, and it's something that one could pretty easily check, would you still get the multifractal structure? I think you probably would, but if you randomly drew from some distribution of 100 different things recursively and said, okay, now let me just randomly draw for one of these 9 blocks that I divided into 9 again, and for one of these I randomly draw, and I do that, do I still get the multifractal structure that you're looking at?
I mean, there are many
Because
aspects.
that would be closer
To reality. I mean, sure, if we want to start picking out what is wrong or what more could be done, right? I was only telling you when the network grows, right? So no rewiring, no nodes die, things like that, right? I was only working with 4 parameters, right? I mean, there is many more different aspects you could look at, and sure, you would look at them if you would want to do something else.
Yeah, certainly the Kronecker model is not an if and only if.
Of course, I mean, it's the only model, right?
Satisfying if.
Can you consider it as a generative model for graphs?
Yeah.
I don't think it's for us.
It's a distribution over graphs at the end, right? Yeah, it's a generic model for graphs.
So can't I just observe data and compute a posterior distribution over parameters and say that, you know, that's what parameterizes my graph?
Sorry.
But I'm giving you the MLE of this distribution.
Have you tried to follow, if you look at your historical
One last
data,
question, so Yuri can catch his breath for a full afternoon.
so you have
Right,
this
and
historical,
after this he comes to
you have the historical data, and you forget the last year. Now you form your Kronecker model, and now you look how it predicts the last year. Have you done that?
I haven't, and the reason for that is because you would, and maybe I should, but one thing is that, right, I'm sort of increasing my set of nodes, right? So I would really need, so one problem with Kronecker is also that, right, you can have 2 to the k nodes only, right? Or 3 to the k or whatever, right? So real graphs don't have that. And now you can ask me, how did you do your experiments, right? And I can say, you know, I padded the adjacency matrix with zeros there, right? And so on. So maybe I should have done that and see how it does. But it should do well, especially like in the densification. that will be there, and that should match, and the diameter will remain constant. So if the graph is late in its evolution, I will also match that. Okay. But maybe I should do that. Okay, thanks a lot.